Welcome, welcome, my lovely students. I hope you are having a happy Thanksgiving week. Um, Hopefully I am too. So what we have to cover is nonlinear systems. So hopefully you spent Monday learning about 3 variable systems. So now we're going to shift back to 2, but some of them are going to be squared or square rooted. So same idea. We're still figuring out where do these graphs cross. It's just now the graphs aren't always straight lines. But a lot of the stuff we learned way back when we did systems of equations the first time are going to apply here. So a nonlinear system of equations is a system in which one or more equations is nonlinear. Go figure. Worst definition ever. So it could be only one is nonlinear or both of them are nonlinear. The way those kind of graphs interact causes us to get more than one solution at times, but not an infinite number the way we did with lines. So when we look, the first picture here is a circle and a line intersecting it, and we can see the line crosses it at 2 points. I could craft the line to only cross it at 1 point as well, so it doesn't always have to be 2 in this case, or if I crafted the line like really high up, it wouldn't cross the circle at all. We can get 4 solutions. That is 2 ellipses being intersected. Or we could get no solution at all. We have a parabola deliberately positioned well above a little circle, so they never cross at all. But if I started moving that parabola down, I could get 1, 2, 3, or 4 points of intersection. Couldn't get more than 4 though, I don't think. But if you can draw me a picture of it, I'd be impressed. You can even have an infinite number that's not the same as all real numbers, but you have to have a periodic graph usually to do it. So something like the sine graph that we haven't talked about at all, it's trig function, but it goes on and on, up, down, up, down, up, down forever. And if I just crafted a line that crossed it, then it's going to keep creating more of those points where they cross. So before we learned about graphing, we learned about the substitution method, and we learned about the addition method. You guys are probably, this is going to head towards matrices, which uses a fancy thing called Gauss-Jordan elimination. And it's kind of like a weird formalized way of doing the addition method a whole bunch. So on the homework, it does direct you to use a particular solution style. I didn't bother. So I'm going to do 2 of them with the substitution method, and the reason I'm doing that is because one of my equations here is linear. When one is linear, I can solve easier, get a single variable by itself, and then I just substitute into the other to solve. Alternatively, and on Alex, it is also going to ask you to graph these things. Now, graphing x squared plus y squared equals 50 wouldn't be so nice because then the radius is square root of 50, it doesn't graph nicely. But giving you x squared plus y squared equals 100. That's a circle with a radius of 10 centered at 0, 0. Putting some offsets in there, maybe it's x minus 2 squared. So just don't be surprised. They'll expect you to be able to graph parabolas, circles, and lines. And you should be able to do that by now. But if not, come to office hours, ask. So this one, the first one is linear. It is a line. The second one, x and y squared, are both squared. But there's no other numbers next to them, so that's how I know it's a circle. Really though, all we want to take away is if both x and y are squared, then it gives us the possibility of up to 4 solutions typically. All right, so solving with substitution, I need to take equation and get a variable by itself. The second equation with the squareds, if I was going to get x by itself, I would have to square root. Same thing with the y. I don't like square roots, so I avoid using them as much as I can. So top line, I have 2x. If I was solving for x, I'd have to divide by 2. Don't want fractions. So we are going to solve for that y in the first equation. So we have 2x plus y equals 5. And I'm just going to subtract 2x from both sides of the equation. Now you could write this negative 2x plus 5 or 5 minus 2x. The order does not matter. I'm going to go with 5 minus 2x just because it looks more appealing at this moment. Now what this is saying is y is the same as the thing 5 minus 2x. So if y must be the same as that to figure out where these two systems intersect, where they are the same, so y has to be this to satisfy one system, I'm going to plug that into the other so it's satisfying both. So in place of the y in our circle equation here, we're going to put 5 minus 2x, which yes, does mean we're going to have a crazy looking box method. So I'm going to write that over here. So the x squared plus y squared equals 50. And now we are just going to put this in place of the y. So now we have x squared plus thing squared equals 50. But thing is now 5 minus 2x instead of the y. So this is only in terms of x. This is solvable, a little on the ugly side, but it's solvable. So I could do 5 minus 2x times 5 minus 2x using the box method. I'm going to speed it up a little because I hope by now you guys are comfortable with that. So we will have x squared here. 5 squared is 25 minus 20x plus 4x squared. And this is still equal to 50. So we are still going to get a quadratic, so I need everything on one side. So 4x squared and x squared is going to be 5x squareds. We're going to have the minus 20x. And then I have that 25 there, and I want to move this 50 so it's equal to 0. You always want that 0 for anything higher than a linear. So 25 minus 50 is going to take us to minus 25. And that is now equal to 0. Now, we could throw those numbers in the quadratic formula, crunch it out just fine. Odds are very, very strong that this will factor. And there's another nice side note. So we have the 5 in front of the x squared, but look at the other numbers. They're also divisible by 5. So do yourself a favor and divide everything by 5. I am dividing both sides by 5, and I'm just splitting it on the left side so it's into each term. And I will need far more room because I write too big. All right. So this is now x squared minus 4x minus 5 equal to 0. And that is a lot more straightforward to factor. It's got to be x and x. Can only be 5 and 1. And to get a negative 4x, I make the 5 negative and the 1 positive, so it also multiplies to the negative 5. So this gives us x minus 5 equal to 0, which means x is 5. X plus 1 equal to 0, which means I minus the 1 over and I get x equals negative 1. All right, so I have 2 lovely x answers. I just did a crap ton of work to get there. We're halfway done. When we're solving a system, a solution is a point. An ordered pair point. So for every x I find, I have to find the y that goes with it. Or sometimes we're going to solve for y first. For every y I find, I have to find the x that goes with it. And sometimes you can get more than one. So it is possible to plug in x equals 5 and end up with plus or minus 2 as an answer. But the points have to work in both systems. So when you have a choice, when one of your equations was linear, plug the numbers back into the linear equation because you're likely to get 2 points in the nonlinear and only one of them works on the line. Now, if they're both nonlinear, then it doesn't much matter where you plug them in. This is also why it helps to graph them because you see roughly where the points of intersection are. All right, so let's start with our first one, x equals 5. And look, I already have y equals 5 minus 2 times whatever x is, in this case, 5. So 5 minus 10 is going to be negative 5. So that gives us a solution of 5, -5. That is our first solution. Now, our other one, we're going to check x equals negative, not check it, we're going to solve and figure out what the y value is that goes with this. So we have 5 minus 2 times -1 becomes plus 2, so we get 7. So when x is -1, y is 7. And there's our other ordered pair. Both of those are equally correct. We have no way to choose one over the other because we have no context for this problem. And I can write context to make one make sense over the other, or make them both make sense, or make them both ridiculous. So as practicing mathematicians, you just box them both and call it good. Alex wants you to write it in a solution set, so you have to start with the curly brace. Then you write one of the ordered pairs. Then you have to put a comma. Then you write the other ordered pair. And the order you write the ordered pairs in, I could write -1, 7 first, but I can't swap the orders in the pair. I cannot write 7, -1 and expect Alex to know what I meant. So when you're solving these, especially if you get y values first, make sure you write the ordered pairs x, y. All right, so we solved for one variable, plugged it into the other equation, arrived at some values, went back to the linear equation, and found the points on that line that matched with the values we found. And then you write it in curly braces. So now we are going to do it one more time, but now we have a very interesting looking, yes, sure, square root of x. But we can handle this. Substitution, like if you're not sure, go with substitution, plug in what you got. So in this case, I have y equals the square root of x. Well, it's already solved for y. Why not just go with it? So I am just going to take this square root of x and I'm going to put it in place of that y. So this will now become, it is still x squared, but now it is plus the thing that was y squared, still equal to 90, and the thing that was y in this case is now the square root of x. So square root of x squared is just x. So we have x squared plus x, and then I'm just going to move the 90 over at the same time because it's a quadratic. Now again, 99 times out of 100, these are going to factor because Alex does not want to have to deal with you guys putting in decimals and where to round them and all that. So if you get a quadratic, expect it to factor. Now, if you're comfy using the quadratic formula, plug them into the quadratic formula. There's nothing wrong with that as long as you are consistent at getting it. But we need a pair of numbers close together so we get a difference of 1 that multiply to 90, so 10 and 9. So I make a positive 10 and a negative 9. 10 minus 9 is positive 1. 10 times negative 9 is negative 90. So there is our lovely binomials. So we're going to get x equals negative 10 and x equals 9. Now, the numbers we get have to work in both equations. So I could plug negative 10 into the first one and solve for y and have a couple values. Yes. But again, don't go with the squared. Go with whatever the weirder equation is for the square root. Can I plug negative 10 in there? I mean, like, I can write it. Y equals the square root of negative 10. And then what happens? Like if you type this on the calculator, it goes. This is technically an imaginary. When we ask you to solve systems, we only want real answers until you get to like way high level math. So this, we toss it out because we didn't get a real answer out of it. So now we're going to go with x equals 9. I'm going to go back to the same equation, y equals the square root of 9 now. Now, don't be fooled here. It is very tempting to think, oh, I'm square rooting. I put the plus or minus. We did not put this square root into the equation. The equation came with it already. So whatever we see is what we get. If we don't see a plus or minus, we don't get to throw it in there. This is just the positive square root of 9. So the only y value we get is positive 3. Now they could have written y equals the negative square root of x, and then our only answer would be negative 3. But here we just get 9 and 3. X equals 9, y equals 3. So the ordered pair then is 9, 3. Now, me personally, if you just wrote x equals 9, y equals 3, I'm ecstatic you got to that, and I'd be happy. But here you're going to start to see more than one ordered pair. So it is helpful to write the ordered pairs as ordered pairs. Because if you just write x equals 9 and x equals negative 10, and then you find y values that go with them, like it's not always obvious which one goes with what. So the ordered pairs do give a more logical answer. All right, I'm going to cut this one here, and in the next one, we'll start talking about the addition method.